All right, so this is the Hacking Mobile Devices class. And I should mention I was looking to see what project to demonstrate, and the one I wanted to demonstrate today was the very last project. But don't bother doing this. You steal secrets from Keeper on Android. The problem is, when I wrote this, you had a rooted device, like a Genymotion device, that was rooted and had access to the Google Play Store. So I wrote the project saying you have to go to Google Play, and then you have to use Frida, which requires your phone to be rooted. Now this semester, most of the students are using Android Studio, which means you have either a rooted phone or Google Play, but not both of those on the same device. So what I want to do is pull Keeper off my phone and store it on my website so you can put it on there. But the problem is it is in many pieces. Modern apps are not in one APK file. They come as like 3 or 4 APK files, and it is not simple to install an app like that using ADB. However, it supposedly can be done, and I spent most of today trying to do it, but it's not working yet. So don't bother with 521 is what I recommend. It's not due for several weeks. And I'm going to have to work on it and try to make this easier. Anyway, and I guess the same thing is probably going to be true of 520. So I'm not going to have a demonstration of a project tonight because the ones I want to work on, I think I need to redo for the latest generation of emulators we're using. So I'll just do the lecture, and the lecture is chapter 9, which is writing secure Android apps. So let's take a look at that. And that goes here. And this is basically, we've talked about all these vulnerabilities one by one, and this talks about the defenses. So it's just looking at it from the other side. So the common vulnerabilities that you have in web apps and mobile apps, which are very similar, is code injection, where data that comes from the user is misunderstood as code. Logic flaws, of course, are always there, where you make some kind of mistake in your thinking. For example, when you can bypass the lock screen by making an emergency call and then going back, that's really a logic flaw more than a technical flaw. Storing things in insecure storage like the SD card, and have misconfigured apps or communications, and logging. These are common vulnerabilities. So we'll talk about the general security mechanism you can use in 4 categories. So least exposure is the first one, and the idea here is try to minimize the attack surface. This is a general fundamental security principle. This is why you remove demonstration code from your web server and so on. You just try to remove anything you're not using. You try to lock it down. So find out what entry points are not necessary. For example, in that trucker story, they said these trucker devices have Bluetooth and Wi-Fi turned on all the time. And maybe you don't need Bluetooth, in which case that would be an attack vector that you could remove. So remove the entry points you're not using, and then put security checks at the necessary entry points. This is how you minimize the attack surface, so there's less ability for attackers to get into the device, to insert anything in. So you consider your components. The safest case is shown here, where you have only one exported activity, which is the original launch primary opening page, and nothing else. Don't export anything else. So the only way in, there's only one way in, the main activity, and then only after you log in or inside the app do you have access to the other features of the app. Now sometimes you do want your app to take signals from other apps, but if you do, you have to be careful and lock that down, because that's a possible entry point from a malicious app. Data storage is a big deal. Don't store unnecessary things like passwords. Like I say, about half the apps do store passwords in local storage, and this is a very bad practice because it can be stolen by people that can get access to the phone. For example, if they root it and then read the hard drive from a phone that's just left lying around somewhere, read the SSD, and you really shouldn't be storing passwords on the phone. If you do need to store secrets on the phone, you should put them in the Android keychain, where they're encrypted by the operating system and relatively secure. So you have data coming in from other sources. You can bring data in on the SD card, the internet, Wi-Fi, and Bluetooth. All these can send signals into the phone, and therefore they're all possible attack vectors. So whenever you get data, you should verify it with whatever is appropriate. Validate it, make sure it's correctly formed, maybe encryption, maybe a signature. Whatever the data is, you should test it. This is the zero trust model that we're all supposed to be moving to. Anything that comes in, you should not just trust it, you should test it to see if it's malicious before trusting it. All right. In general, your app should not have more permissions than it needs. Obviously, that's another security barrier. If your app doesn't have very many permissions, then even if your app has a security flaw and an attacker is able to abuse it, they won't be able to do as much harm from lack of permissions. So avoid dangerous permissions like install packages or using system permissions, which would clearly give the attacker more power. This way, the attacker can take over your app, and then they have another barrier to escalate privileges before they can get further. Your APK file. As I'm saying, APK files are just zip files that contain many other files, and you can include whole directories of other files in addition to the bare minimum to run your app, and sometimes it includes other files like SSH credentials and so on, just like GitHub repositories often do. The developer develops something, there are some secrets in there, then they zip it up and deploy it, and they don't realize that some of the stuff included in those folders was private. It's one of the common mistakes to make. So some security mechanisms. You review your entry points. So on create is what launches the main activity. On receive is what comes in for broadcast receivers. You can look at the methods that call these system calls, and those are the things that are connected to these parts of the app. Content provider is a database, so it has the usual SQL type things like query, insert, update, and so on. And service is on start command is how you bind to a service. So these are functions you would look for in the app to find out how is data entering these various activities, and then you can see whether the data is properly validated before use. If you export components, you should limit them with permissions, so you don't just export them to the whole world, but only to apps with the same signature, which means apps from your company, if you can do that. If you have a suite of apps like Microsoft Office that want to work together, you could make it so only other apps from your company can get in there, and that would be a lot safer than letting every app get in. If you really want to offer something for public use, like you want web URLs to open in my app, then you're taking totally untrusted data, and you've got to be very careful to filter it. All right. So activities, by the way, your recent app list, you've seen this on the phone. When you click the square, you see a little image of each app. And in principle, that is just always available. So if that image had something like a password or something, that would be a possible way for data to sneak out. We call it task manager snooping. So you can put in code to show a blank screen for your app instead of an image of the app shrunk down, or you can even remove it entirely from the list by designing your app. So that's a thing to be aware of. Tap jacking, we've talked about. If you put a transparent screen on top of a visible screen, and now when people think they're tapping things, they're actually tapping invisible buttons that do other things. Like you think you're playing a game popping balloons, but you're actually installing an app, downloading it, approving it, and all that. So there is a filter touches when obscured attribute you can use, which will prevent that, so that it is not possible for a touch to go anywhere other than the actual visible screen. I don't know why they don't just leave this on all the time by default. But anyway, you can put it in your app this way so that your app will not accept any touches except when it's really visible. And you can consider the dictionary. This is in Apple, there's the famous autocorrect that irritates people. And in principle, there's a dictionary where if it's seen a word before, it remembers it and checks the spelling later. So you might not, there are words you don't want to go in there, like your password. So you can put that here. If your input type is text visible password, then it will not store what it sees in there in the dictionary, which is a good security measure. Fragments, I use fragments. I should show them on a web page. If you go to my web page here, and you click like the news link, maybe not that one. Some of these used to be fragments. The ones on my page, I think they're fragments. This one here, if you go to, say, slides, then what this does is it scrolls on the same page, and you can see it up here. It just added a pound lecture. This is called a fragment. It is a bit of extra data added to a URL, which can redirect you to a spot on the page. And those are called fragments, and you can put them in activities, and they can move to pieces of an activity, just like pieces of a page. So that's what they are, and there are attacks where you stick in fragment injections that are misunderstood and have unexpected results, like something. I'm not quite sure what you can do, perhaps code injection, but that's why they're blocked since Android 4.4. And if you wanted to allow them, you could use this code to allow particular fragments in but they turned out to be unsafe. All right. So there got to be secure trust boundaries. You know, you have an app, and your app has a login screen, and then there's parts of the app you can only get into after you log in. And that's if you only had a few activities, you could probably handle that. But as your app changes and grows and gets bigger, like remember that Chinese app that had like 200 pages of screens, it's very likely, let me just refresh this one over here that is irritating me. It's very likely that you will have portions of the app that did not correctly check the permissions. So the right way to do this is have an app-wide authentication variable. And the same thing applies for web apps. You should have a central authentication provider, which is always used for all the secure stuff. That's the only way to do it that you can maintain as you go forward. Then you have a standard test. The same thing is true of APIs. It's extremely common that APIs offer a dozen or more functions, and some of them forget to check authentication, so an unauthenticated user can do things they shouldn't be able to do. It's very common. And in all cases, the right answer is to have one authentication process, and then every use of the app has to check the authentication first to see who are you, and are you allowed to do what you're trying to do. You can mask password displays just so people can't look at the phone. You can put in this attribute and then it will hide the characters. I think the default is on phones, of course. It shows the one letter you're typing but no other letters. So it's harder for somebody watching to get your password. And then browsable activities I mentioned, these are ones that you can use from web browser. You click a link in a web browser and it opens the app right away. And that's of course highly valuable for attackers because it's very easy to trick people into clicking links on web pages. So if you do use browsable, then you have to be very careful considering it's very likely that there will be malicious data coming in. And content providers are the databases that store data. They used to be exported by default, so if you can turn that off, but usually you want to target a later API anyway. I don't know how many people are still using these really old APIs. But anyway, then you wouldn't export your data to everybody. And then you have SQL injection, like we talked about. What you ought to be doing is instead of putting user data directly in a string, which is then parsed, you use this part where you use question marks to mark the place where data goes, and then you feed the user in here. So that's why the data is treated as a data object. It is not mixed with code, and there's no input that could be misunderstood as code. Otherwise, you have SQL injection. You can inject SQL statements. Directory traversal is another common one. If you ever take a file name for something, the user can put in .. and move up and out of the expected folder into other folders where they shouldn't be going. And if you use the get canonical path method in your app, that will resolve it to a canonical path, which means starting from the root of the system, /users, /data, /whatever it is, the one unique path to get where you're going, and then you can make sure that it starts with the right stuff. Right, so this is one example that does this. This is going to parse the file descriptor, and so it's going to go here and get the canonical path, and then make sure the canonical path starts with the base folder. It'll only accept it if it's in the expected location. This is the way to do it. This is a secure way to do it. Then if the user puts in things like .. they'll work if they remain in the allowed area, and they'll fail if they go outside the allowed area. And the pattern matching is an issue. We've seen this in the projects. If you use subpath, and Android path equals subpath, then it'll apply to entries in subpath but not subdirectories. Android path prefix would apply to everything that starts with subpath, which is probably what you want, this folder and all the subfolders. And if you have a pattern, you can use wildcards too to specify this, path pattern. The path is the really dangerous one. If you use the path to define your permission, then it has to be exactly that path and nothing else, and that is usually not what you want. You usually want path prefix. You mean that path and everything below it. So, and these secret codes, we talked about secret things you can dial to do things like reset the phone to factory default or something, and they're in the Android manifest. So if you have secret codes that do something, you cannot count on them staying secret. They're not that hard to find, and there are online apps to find the secret codes of apps. So don't imagine that that stuff is really going to stay hidden for long. All right, let's try a Kahoot. I don't see any more comments in the chat. This is 9A. Here we go. All right, looks like we got everybody that's coming. All right, so what defense stops tap jacking? Yep, filtering touches. When obscured, that's the point. So when you press things, it will not accept it if there's something else in front of it. All right, what component has fragment injection? They're part of activities, like they're part of web pages. It refers to some location on a page and turned out to be risky. How do you stop SQL injection? Get prepared statements that insert the data without putting it directly in a line of text that is parsed, but insert it as a data object. All right, so which path permission does not protect subfolders? Which is kind of a shame because it's probably the simplest one, the most obvious one you would probably use, but it means the path has to 100% match the path in the Android manifest for this permission to apply, and therefore it's usually not what you want. All right, let's go on. So, if you're going to store files and you don't want other apps finding them, you can explicitly set permissions to your file. Make it private, which is, I think, just Unix permissions, read, write, execute, and so on. You can use encryption if you want to. If you're going to, AES is the best for symmetric encryption. You should not use electronic codebook mode. RSA is one good option for asymmetric encryption, although we should be worrying about post-quantum encryption these days, although Lord knows. Anyway, if you want to hash a password, you need to have salting and stretching. Salting is where you add some extra random letters to it, and stretching is where you do many rounds of a hash function to store passwords. But in general, you really should not write your own code to do any of these things. You should use standard libraries. It's much safer. Writing your own code, you're likely to make a mistake, and when security flaws are found, the standard libraries will get updated, but you probably won't be able to update your code easily. So it's better to just use standard cryptography code instead of trying to write your own code. This is considered, rolling your own crypto is considered a fundamental flaw, fundamental mistake. Random is a problem. The simple random number functions in most languages, including Java, are predictable. They're seeded and they have a predictable set of numbers to the same seed. Now that might be what you want if you're trying to do something like have a one-time token where you have an app on the phone creating a series of numbers and you want to create the same series of numbers on the server, but it's not normally what you want for cryptography. You want a real random number. So there's a better method called secure random that will really be more random. There's quite a few security flaws that come from so-called random numbers turning out to be predictable to any extent. And so here's random with a seed, and you can just run it online and see that it'll give you the same answer each time you run it. It's easy enough to test. Now, most people don't want to type in a key. Obviously, you want to type in a password. So what you do is you use PBKDF2. This is password key-based key derivation function. 2 is the common one used. And all it does is it runs it through a hash function like SHA-512 or something many times. And then picks keys out of that, picks bits out of that to make a key. So this is a way to generate a cryptographic key from a password. And the same thing is used by almost everything, including Windows encryption and everything else. Once you get a key, you should store it in Android Key Store if you're going to store the key on the machine, not some ad hoc place you choose. But the Android Key Store is the safe place to store secrets on the phone. Probably the safest place. If you want to, normally your files should be private, only visible to your app. But if you want to share them with another person, then you need to give them read-write permission for your app. This only applies to the document folder. So you have one folder and you let other apps see what's in there. That's an option. All right. And then communications. HTTP is very unsafe for any purpose. You shouldn't be using it at all because anybody can alter the data and inject things like scripts and so on. So even if you're loading static content like images over HTTP, it's still not safe because the attacker in the middle could add dynamic content to it. HTTPS is better, but you have to actually verify the certificate with trusted certificate authorities, and as we've seen, a lot of apps fail to do that. Certificate pinning is a way to make it even more safe, where you don't even accept the standard test with the certificate authority, but you add another test of your own. This turned out, however, to be a problem and is generally falling out of favor because suppose you pin it to use only a certain certificate authority provider, and then you want to move to another authority provider. It's hard to do. How do you update the app? So HPKP is the header that's replacing this, although apps still use certificate pinning. Web pages don't do much, but all right. So to move data from one app to another, there are a lot of people that try all sorts of ad hoc techniques. The best way is to use the Android API. You can use intent filters where it listens for intents. And in more recent Android versions, they've added more sophisticated ways to do this, something called chooser targets, shortcuts, and direct share targets. These are ways to create an object that shares data from one app with another, but only with certain apps, so it's more controlled. You can use network sockets or the clipboard too, but they're much less safe because other apps can, in principle, read that data. And then web views, I mentioned many times, web views is used to put a browser inside your app. And the problem is, then your app often fails to maintain the security required of a web browser. You obviously should use HTTPS instead of HTTP. You should disable JavaScript if you're not using it. And JavaScript interface is considered quite dangerous, where you let JavaScript run in your web view and you let the JavaScript run Java commands on the phone. So it's like a shell command injection right from the web page. There shouldn't be any plugins in modern versions of Android anyway, like Flash and all that stuff. You can block file system access, and you should validate any web content before using it, because, of course, all the web attacks can be coming into your phone now. So the Android manifest has some security-related features. You can determine whether to allow backups. So when they make a backup of your phone, they get all the data. You can turn that off, and then people won't be able to back up the data, but an attacker who gets the phone won't be able to get the data by using backups. And then there's debuggable, whether it's allowed to debug that app. I should have a project where you debug an app. I haven't got it in here yet. I would like to play with that, but I never got around to doing it yet. All right, and so you should target larger SDK versions for security. That means people with really old phones will not be able to use your app, but they probably would not be safe to use your app on those really old phones anyway. So for higher security, you would force people to use newer phones by having a higher SDK, min SDK version. Android 9 is 28 and above. This gives you a lot of security. Your DNS is encrypted. All your network traffic is encrypted unless they work hard to send it in clear text. It's possible, but it's not the default anymore. And it has separate web view directories for each process, so one web page cannot steal the cookies from another web page. So those are good security features. And Cloudflare had a deal to get its encrypted DNS using their provider, which does DNS over HTTPS. And logging, of course, generally it's recommended to not use any logging at all in release builds. It should only be in your test build. So use a centralized logging class. You can easily disable it. And ProGuard, which is the free security module in Android Studio, can remove logging code. However, almost every app I've ever seen does in fact still have logging on, and often it leaks secrets in the logs. Native code is code that's written in like C or C++ and compiled down to real assembly language, real machine language on the phone. It's not Java going through a Java virtual machine, and therefore it's notoriously difficult to secure. It tends to be written in C, so it's got all the old-fashioned vulnerabilities like buffer overflows and format string vulnerabilities and so on. So if you want to do that, you need the old-fashioned security features that apply to like Windows apps, things like address space layout randomization, position independent executable here, non-executable areas of memory, and so on. A canary to detect when the stack is overflowing, and relocation read-only, which stops the app from writing the relocation records that lead to the system libraries, which we use extensively in 127 to take over Windows machines, and so on. So there's a lot of, here's the mitigations. This presents global offset table rewrites, which are a common way to take over the phone, where you change the address of a system call. So now when you try to call some function like exit, you're really calling a malicious function instead. This is run path, allows users to load modified libraries like dill injection on Windows, and you can prevent that with this mitigation. And the advanced mechanisms. I don't think this still works in modern versions of Android, but this is one you were able, in older versions of Android anyway, if you were going to install an app that was going to define a new permission, like Skype is going to define a new permission Skype, you could make your own app that defines a permission with the same name first. And then when the Skype app installs, it will recognize, oh, this is not a new permission, so it will just connect to the old permission, which can be set in a less secure manner. So that was a downgrade. You would inherit the permission level of the previous app. And your app can check for that, but by default it didn't. If you install an app and it declares a permission in the manifest, if it finds that that permission is already on the phone, it just connects to the existing permission, which might be more open. So that was an issue there. And if you have non-exported components, you do not export things like activities and content providers. If you have root permissions, you can still interact with them. We've seen this before, and this is how that automated scanner worked. It loaded the Chinese surveillance app and had root permissions. It could just open every page. All right, you can have a request token that prevents that, where you stored it somewhere and intents have to have that token to run. So even the attacker with root permission will send a request to open the page, but they won't know the token. Now, of course, they can read the source code and figure it out, but it slows them down. In principle, you can't have too much security when they can read your source code. All right, and that's what slowing down a reverse engineer does. You can do things just to make it harder to read the source code. That's obfuscation. So ProGuard is free, and what it does is it just changes most of the names of the methods like A, B, and C, all your functions in your Java code, so it's harder to find them. But in practice, a whole bunch of them still retain useful names like credit card number, password, and so on. -O is, I think, one that had a free trial. -O does this. Every string turns into like 20 random characters. So nothing is ever named password or credit card number or anything like that. And that, of course, is irritating. Now, you can still get in. What I did was write Python code that would log every variable everywhere. And then you run your app, and then when you log in, you look in the log to see what's there. You still hack into things this way, but it slows you down when you can't have any readable strings to guide you to the interesting part. And root detection is quite a challenge. In the last week, I was showing you a project where you're trying to defeat root injection, and the root injection was so rudimentary, it didn't even work on API 33. So here's common root detection. Look for SU, super user. See if your ADB shell can run as root. See if it is running as root. Look for other packages, these names. That's what root detection is. It just looks for common ways of achieving root, and so a more sneaky way of achieving root will evade the root detection. You can also detect an emulator, and I mentioned before, if you do a class where you research Android malware, you have to use a real Android phone because almost all Android malware does detect emulators and refuse to run. So it just looks for clues. Similarly, it's very easy to tell when you're running Windows in a virtual machine. The network adapter has a different name. There's keys in the registry and so on. So it's not hard to make malware that would detect when it's running in a virtual machine. It's just not as common in the Windows world as it is in the Android world. And you can have debugger detection. You can detect to make sure the application is not set as debuggable. And this is something your app really ought to do. Your app ought to say, I'm sorry, I won't run on a rooted phone. I'm sorry, I won't run on a phone that has debugging turned on. Those are things you really ought to be doing for any security app, any secure app like a banking app. And you can just check for tampering. This is the #1 most common vulnerability that we've been exploiting in the projects. You can download the Progressive Insurance app, you can modify it, put in a modified app, and it still talks to the Progressive server. So you can get people to use that and think it's a safe app when it's not. And that's ridiculous. You can check the signature of your app and refuse to use it. Say, no, this app is not signed by Progressive anymore. Therefore, you pop up a box and say, you cannot use this app, you have to update to the right app before you can use it. Everybody should do this. Almost nobody does, which is true of most of these security measures. So let's try another Kahoot. 9B. So I gave a bunch of DEF CON talks talking about all these ridiculous security flaws and how people don't care. Hasn't convinced them yet, but this is the way security always is. You start by complaining about things, and then it takes years to convince the industry to upgrade their processes. It's a lot like political activism. You complain that people are polluting the water or something, and again, you have to go through years of resistance before you actually get a change made. Looks like we got everybody. All right, so what defense prevents stack overflows? put this number at the end of a stack frame, so if one of the string variables is overflowed, it will change that number, and you can detect that the memory is corrupt and stop the app from running. It's available in every operating system like Windows and Linux and everything too. Stack canaries are the common defense against this. All right, what function creates a key from a password? Yeah, this is the old-fashioned one, PBKDF2. The new one I think is called scrypt, but they're very similar. Just runs it through a hash function a bunch of times. All right. All right, what defense makes small e code difficult to read? Yeah, this is obfuscation. Obfuscation is like blurring something. It doesn't actually create a barrier that prevents you from getting in. It just makes it harder to understand to hopefully slow you down. This is really common in PHP malware. People rewrite, and JavaScript malware. They write it, instead of spelling out commands, they put up a variable with 100 random letters, and then they pick letters out one by one, just to make it hard to read, hard to understand, to slow down reverse engineers, and to prevent automated processes from detecting malicious patterns of code. All right, and what makes HTTPS more secure? Certificate pinning checks to make sure the certificate is right, even beyond the normal check, verifying with the certificate authority. Shows one twice, and shows Pete. And I bet Tark is the other winner. So, I'll turn off this recording.